So how do we make a DC to DC converter look like a positive resistance? It's very simple, shown here in the curve. We have the input current and input voltage to a DC to DC converter, the model which is coming up later. In this particular case, I'm showing it operating from 0 volts to 40 volts in this curve, realizing that most converters would have an undervoltage lockout and they really wouldn't look like this because the control circuit wouldn't start until maybe 20 volts or so. But in this model, we're allowing it to run from 0 up to 40, and all I've done is fix the PWM duty cycle at max duty cycle. So the input current follows the input voltage as a straight line. That's how simple it is. So you saw the curve with positive resistance with a fixed duty cycle. Here we've closed the loop and we're showing what the converter input characteristic, the DC characteristic, looks like when you've got closed loop control. Now until the loop is able to close and regulate, we have to have enough voltage. Looks like we need around 37 volts here for the loop to close. This is a 30 volt output buck regulator. So up until you reach the point where it can regulate, it looks like a purely resistive input. Increasing current, linear with increasing voltage. Then the loop closes, and now it's a constant power device. And so you see the resistance going down with increasing voltage. The negative resistance characteristic of the DC to DC converter is right here. So here's the problem. You connect something with this characteristic to a solar array, and you've got double valued points of resistance all along this curve. And again, we realize that there's an undervoltage lockout, so the converter may not really start up till 20 or 25 volts or something, so this curve may not look exactly like this, but it'll definitely have this characteristic. And this is an unstable condition when you connect this to the array. So you want it to look resistive when you get to the peak power point on the array. So now let's look at what we're talking about. I think some of you have seen this curve in which I have the voltage versus current this way. This may give some of you heartburn. You're used to seeing it IV, but here we have a VI curve. Same information, just plotted a different way. Solar array voltage and power, as we've discussed. Down here I tried to plot the solar array resistance and the DC to DC converter resistance with that input characteristic. You can see the solar array resistance coming down. It crosses the DC to DC converter resistance right here. So anything above to the right of this point would be reasonably stable. Anything to the left of this point is definitely going to have a problem because the resistance of the converter is less than the array. And so you're going to have this big voltage division where you just simply cannot get the power out of the array that's needed by the DC to DC converter. Let's look at this in another way. Okay, now we look at the curves with an IV plot. So the current's on the vertical axis, voltage is on the horizontal, your normal solar array voltage current characteristic, solar array power curve, and then I'm plotting the solar array resistance and the DC to DC converter input resistance. And you can see right here at this inflection point, the converter resistance is less than the array resistance, which is around the 40 something watts that I've shown in the previous plot. If you go on this side, converter is higher than the solar array and everything is probably stable. But if you go past this point right here, you're unstable, the array resistance is quickly climbing, and you're not going to be able to produce the power you need. Same information as the previous curve, just a different way of showing it. So this is a model used to simulate the characteristics shown. This is the Basso model. He has many models, but this is a switched average model, a state space average model that he's created many different devices for. This particular one is a discontinuous mode, voltage mode, buck regulator with a 25 microhenry inductor and a 500 kilohertz switching frequency. The terminals A, C, P in control stand for active, the common output, the passive output, which is simply ground in this case, and control, which is a 0 to 1 volt duty cycle control input. That input is scaled from my air amplifiers, which are 0 to 2.5 volts. I do this little trick with this behavioral voltage source with this conditional equation. I take my air voltage, divide it by 3. If it's greater than 1, I clamp to 1, because that's the maximum duty cycle of this device. Otherwise, I just take the air voltage divided by 3 and let it regulate. There's a partial listing of Basso's model with the model name, the symbol, the pin names, etc. Again, this is a very powerful model that he's created. You can use it for DC analysis, small signal analysis, transient analysis. So it's really a very powerful tool, and you should be using this for your power supply simulations.